Okay, today we're going to be going over the lesson about how to graph systems of equations. I'm going to be going through the lecture notes, and you should be able to download this page within Canvas if you'd like to print it out, or I handed it out in class. But as you follow along today, hopefully you should get what you need in order to do your homework and finish up this unit on the chapter. To start out with, we've got a little bit of vocabulary that we need to review. A system of linear equations is just a set of, let's see if we can write here, set of two or more equations in two variables. So, and we'll look at several different ones, but we're looking at two or more what we call linear equations, so we're just looking at equations that have x and y in them, basically. A solution for a system of linear equations is an xy pair that makes all the equations true. Now, because we can use graphs in order to show equations, we can look at graphs in order to identify solutions of linear equations. If we're talking about just lines, which is what we're going to start with today, when we're looking at two linear equations, we have two graphs of lines, and there's a couple of different ways that these things can be represented. In this particular case, notice that the lines cross or intersect. If the two lines intersect, notice that there's a single point where they cross. That single point is the solution to this system of equations. However, there are a couple of other options that bear noting. One very rare situation that happens sometimes is when you look at those two lines and you try to look at what happens. If you look at their graphs, they're actually what we call parallel. And if your two lines are parallel, there are no solutions in that particular instance because the lines never intersect. So there's no point that will make both equations true at the same time. If the last case here is that the lines are actually equal or the same exact line, in that case, every single point that lies along this whole line is a solution to both of the equations because technically they're the same equation. In this case, we say that there are infinitely many solutions, and it's just every single solution that lies along that line is true for both of the equations as we go through. Now, with that in mind, let's talk about finding the solution to systems of equations. If you have the graph of two lines, the solution is going to be the point where those two lines intersect because that particular point lies on both of the lines and therefore would fulfill them. In this case, we just want to identify what ordered pair that represents. So notice we'll go along this line here. We're at -6 in the x and at 5 on the y. So the point -6, 5 would be a solution to this system, and we can find it by graphing. In this particular one here, notice that our two lines intersect at that point right there on the y-axis itself, and that will be our solution. In this case, the x-coordinate is 0, and our y-coordinate, I believe that's -6 down there. Now, you can see that it's going to be really important. We've been kind of sloppy on some of our graphs in the past, but when we're looking at two equations and we're interested in seeing where they intersect, we definitely have to be much more careful about our sketches so that they cross at an appropriate point. So let's take a peek at a few different examples here so we can see what these systems will look like. If you want to solve a set of equations by graphing, and every single one of your problems on this homework assignment needs to be solved by graphing. Don't just write what the solution is, but graph them both and illustrate what's going on. So in this case, when we're dealing with linear, make sure that your equations are in that y equals mx plus b form. And we can kind of review our linear equation graphing process. The first equation there, notice, has a slope of 3/1 and a y-intercept of +2. So we always start by graphing the y-intercept. So we go up 2 and put a point there. Now our slope says that we're going to rise 3 and go over 1. So to find our next point, we're going to go up 1, 2, 3 and over 1. There's our next point, and then we can kind of connect the dots. As we go down that way. Then we can also graph the points here, or this second equation. So we want to graph both of them on the same axes so that we can see where they cross. This time our y-intercept is -2, which is this point, and then our slope is 3/1. So we're going to go up 3/1, up 3/1, and keep in mind you can do that slope a zillion times. I like to put a couple of points on there sometimes just so that my line's a little bit straighter. And when I graph that, notice in this case that my two lines are parallel. So they don't cross, so there's no solutions to this particular example. And that's because those lines are parallel. Something to keep in mind, in order for lines to be parallel, notice that their steepness has to be exactly the same. And so kind of a good check when you go to draw your graph, if your slopes are the same, oops, not same slope, same slope. If your slopes are the same, your lines that you graph will end up looking parallel, and then they will never cross, and you get no solution. And you can write that as 0 with a slash through it if that makes you happy. Another case here, let's look at these two equations. I can start by graphing the first line here. It's in slope-intercept form, so I'm ready to go. My y-intercept is 3. My slope is -3/4, so I'm going to go down 3 and over 4 to get my second point. And I'm going to take those 2 points and I'm going to graph the line and connect the points like that. Now for the next equation, I also want to graph it. And this particular point here, notice that the y is not by itself yet, so I am not in slope-intercept form. Don't try to draw graphs before you're in slope-intercept form. So the first thing that we're going to want to do is divide both sides by 4 to get the y by itself. When I divide this term by 4, I'm going to get -3/4 x, and when I divide this term by 4, I'm going to get +3. Now, if you notice, this looks awfully familiar, doesn't it? When I went to get that second equation in slope-intercept form, I ended up with exactly the same line, the same y-intercept, the same slope, and so this is that case where you end up with infinitely many solutions. And it's not always obvious when you first look at your graph, but what you have to do is get those into that slope-intercept form, and then if they're exactly the same, then you can actually see that. Keep in mind that any of these graphs, I'm graphing all of these, especially when our equations are lines and in slope-intercept form, they're pretty easy to graph by hand, but it's not a bad idea. You can always graph these equations also using Wolfram Alpha or your graphing calculator and see where those points intersect as well. Here's another couple of examples. Let's look at some of these. In this case, we'll go and we want to graph the first equation first. My y-intercept is 2. So I'm going to put that on, and my slope is 1/1. Remember, if there's no number in front of the x, it's a 1. So here's my y-intercept of 2. My slope is 1/1, and I end up with this line here, up 1/1, so it goes through all of those points as we go down. Again, the neater you can be, the easier this is going to be in coming up with what this solution is. For the next point, I'm going to be looking at a y-intercept of +1. This time I have a slope of 2, so I'm going to go up 2, think of it as a fraction again, up 2/1. Here's my second line, and I can connect the dots and go down this way. And what we're looking for when we're looking to solve the system of equations is we're looking for the point where they intersect, and so my final answer is the point 1, 3. And that's my solution, and this is the graph that I have to support it. So as long as your equations are in y = mx + b form, fairly straightforward, you can get those points without too much trouble. The other thing that's really nice to note is that you can always check your solution. If you plotted everything correctly, this point will make both of these equations true. So if I put 1 in for x, notice I get 1 + 2 is 3 for y, so that checks. In my next equation, if I put 1 in for x, I have 2 times 1 is 2 plus 1 is 3 for y, and it works for both equations. And so that's a great way, especially if your lines are a little wavy and you're not sure if you landed right on it or not. Stick it in, it should make both equations true. That's the whole point of what we're doing. Just as one last example, if you want to pause the video and give this one a whirl, see how you do, and then you can let it roll. I will go through this a little bit quick, and you can see how you did. First equation, y-intercept of -1, slope of -1/2, so we're going to get this downhill trend going here. So there's my first equation. The second equation is y = x - 4, y-intercept of -4, slope of 1/1, comes up this way, and you can see they went right through that point there, and that point is 2, -2. And you can plug that in, and you'll find that that gets both of my equations to be true. Now, a couple of other pieces that might be a little bit tricky. The first one here, notice that we have x = 2 as one of our equations. If the y can't be by itself, Because there is no y, that means that we couldn't get it in slope-intercept form because the slope was undefined. So x equals 2, anytime that you have an x with no other values associated with it, it's a vertical line. So this equation here is this vertical line where x is equal to 2. And so that gives us that first graph. The second graph is of y equals -6. Here, the y is by itself. There's no slope. You can think of this as y equals 0, x minus 6. And so what I have is -6 is my y-intercept. My slope is 0, which is a horizontal line. So x equals are always vertical lines, and y equals are always horizontal lines if there's only one variable involved. So those are kind of straightforward. This time, if we look at their intersection points, they intersect at the point 2, -6. And you'll get a very similar thing here. Your y is equal to 3. That gives me a horizontal line for my first one. My x is equal to -4. X equals is always vertical undefined slopes. My intersection point is where they cross, which in this case is -4 and +3 for my x and y points. The last kind of thing that might give you a little bit of trouble here, well, this one isn't too bad. We're not used to seeing the y not being first. We can turn that around and make that y equals 2x minus 6 and y equals -x plus 3. Keep in mind, in both of these, the y is already by itself. I just like writing it the x first and the plane number second because of the mx plus b thing. It just makes it a little bit easier to keep track of. So pay attention to the format so that I correctly identify what the slope and the y-intercept are when you go to graph them. In this particular problem here, we have my y-intercept is -6. My slope is 2 over 1. So that gives me this equation here. In the next one, my y-intercept is 3, and my slope is -1 over 1. So that comes down this way, and we can see that big spot of intersection occurs at the point 3 for x and 0 for y. Go ahead and try this. Oops. Go ahead and try this next problem right here. Same deal. Again, I really like rewriting it so it looks in that familiar form. It makes it easier for me. Y equals -3/2 x plus 2, and y equals 1/2 x minus 2. And I can graph each of those points there. For the first equation, positive 2 y-intercept, down 3 over 2 gives me my slope. So I can sketch that in. Oh, not very good there, that's okay. And then for my other one, my y-intercept's -2, and my slope is 1/2, so rise over run. We can get that and an intersection point at 2, -1, and we're ready to roll. So your equations there aren't too horrible. The last type of thing that might happen when we're talking about graphing systems of linear equations is that your equations are not actually in slope-intercept form when you start. So for this first problem, for example, notice that I have this x minus y equals 6. The y is not by itself yet. That's a problem. So get the y by itself before you try to graph it. In this case, what I'm going to do is I'm going to subtract x from each side. That gives me -y equals -x plus 6. Again, I'm trying to get that y equals mx plus b form going for me. In this case right now, notice that my y is negative and I need it to be positive. So I can change all of my signs, basically multiply through everything by -1. This will lead me to the equation positive y equals positive x minus 6. And then I can graph that line. My y-intercept is -6. My slope is 1 over 1. My first equation graph is going to graph just like this. For the next equation, again, the y is not by itself yet. That's not too hard to fix, though. I have 2x plus y equals 0. I need the y to be alone, so it's in y equals mx plus b form. And I end up with y equals -2x. My y-intercept is the plane number over here, which is just 0. If there's no plane number without anything, that's just crosses right there at the origin. Here my slope is -2 over 1. Again, always think of that as a fraction. And I come up with that sweet little thing there. And there's my point of intersection at 2, -4. And again, you can plug that point into your equations and make sure that they all check out nice. Go ahead and try again, pause the video for a second if you like. Try to get the y's by themselves in each of these two equations, and then graph your equations when you get back out. When you do that, okay, so when you do the first one, you should end up with y equals 2x minus 1 for the first equation. And for the second equation, you should end up with y equals negative 3x minus 6, trying to get the x by itself. Then we just want to plot them and see how the intersections turn out. The first equation, y-intercept of negative 1, slope of 2 over 1, so up 2 over 1. For the second equation, I have a y-intercept of negative 6 and a slope of negative 3, so I'm going to go down 3 over 1. That becomes so bad that I can't even get on here. So if you're down 3 and to the right 1, we can also go up 3 and to the left 1 to kind of continue that trend. Or you can extend your graph down if you want a little bit. But as you connect the dots and come up here, you should end up with those lines crossing here at negative 1 and negative 3. And so that gives us our next values as you go. All right, with that in mind, I'm going to go ahead and pause this video so it doesn't become too long. In the next video, what we're going to do is look at solving systems of equations when they're not both lines. So when we have other equations and functions involved as well. Hope that helps.